Hello. In this lecture, we will study about the mutual induction or mutual inductance. So we start. Mutual induction is the property of the two coils. Whenever the flux linked with the one coil changes, it induces an EMF in the second coil. As you see, there are the two coils, the coil A and the coil B. Coil A is connected with a battery and coil B is connected with a galvanometer. At the time of make of the circuit or the break of the circuit, current in the coil A changes. As magnetic field is equal to mu naught Ni, due to this, the flux linked with the coil changes. As the second coil is placed close to the first coil, the flux linked with the second coil also changes and EMF is produced. This phenomena is called mutual induction. So mutual induction is the phenomena of inducing EMF in the second coil due to the change in flux in the first coil. Now we are talking about the mutual inductance, which is also known as coefficient of mutual induction. As you know, the flux linked with the second coil due to the current in the first coil is equal to this one. This can be written in this way. M is a constant of proportionality and is called mutual inductance. If current is unity, then mutual inductance is equal to the flux linked with the second coil when unit current is flowing through the first coil. Now another definition, as you know, that EMF can be written as minus d phi by dt. Now put the value of the flux, that is M into I. So it is equal to M into di by dt. Now we will define the mutual inductance, which is equal to E upon di1 by dt. If di1 by dt is 1 ampere per second, then M is equal to E. So what is the mutual inductance? It is equal to the EMF induced in the second coil when the current is changing at the rate of 1 ampere per second in the primary coil or in the first coil. The unit of the mutual inductance is same as that of the self-inductance, that is Henry. Mutual inductance is said to be 1 Henry. From this definition, that is phi equals to M into I. So M is equal to phi upon I, and mutual inductance is said to be of 1 Henry. When 1 ampere current in the first coil produces the flux of 1 Weber across the secondary coil. Another definition of the 1 Henry from the statement, that is E equals to minus M di1 upon dt. Mutual inductance is said to be of 1 Henry when the current changing at the rate of 1 ampere per second induces the EMF of 1 volt in the second coil. Now we will derive the expression for the mutual inductance of two solenoids. Now say it is a primary coil. It has number of turns N1, L is its length, and R is the radius of the coil. This is a second coil whose number of turn is N2 and its length is also N. This coil is connected with a galvanometer and the first coil is connected with a battery. As it is connected with the battery, so the current is flowing through the first coil, that is the blue color coil, the current is flowing. Now, as the current is flowing through the first coil, so the magnetic field is given in this way. The flux linked with the secondary coil, the flux linked with the first coil, and the same flux is linked with the secondary coil. So the flux linked with the secondary coil due to the current in the first coil is equal to B1A, which is written in this way as the B1 is equal to mu naught N1 I1. And you know the relation between the N1 number of turns per unit length and the total number of turns. So we can write it this way. It is a magnetic flux linked with a one turn. If there are n turns, then the flux is equal to this one. We have just multiplied it with the number of turns, and the number of turns in the secondary coil is N2, or you can say N2. So we multiplied this equation with N2, and it is a flux linked with the second coil. And you know that the phi is equal to Mi. So this is the relation. Now put the value of phi to 1, this value. I1 cancel out, and this is the relation. Using the relation, that is N1 equals to N1 into L and N2 equals to N2L, we get this relation. Similarly, we can find out the mutual inductance linked with the first coil when the current is flowing through the second coil. Okay, now see, mutual inductance linked with the first coil when the current is flowing through the secondary coil. The two coils of the same length and same area, the mutual inductance is same. That is, and it is equal to mu naught N1 N2 A into N. If the two solenoids are not air-cooled but they are bonded over some substance whose permeability is mu, then in that case this factor is additional. If the number of turns are different and radii are different, then in area we are using the smaller area. Mutual inductance depends on the relative positions of the two solenoids. Now we discuss the coefficient of coupling. Now there are the two coils whose self-inductance is L1 and L2, and the mutual inductance is M between the two coils. Then the coefficient of coupling, which is termed as K, is written in this way. The value of K varies in between 0 to 1, and K is a unitless quantity. Value of K depends on the relative orientation of the two coils. The two coils are placed in this way. They are placed in this way. They are placed like this. In this case, the value is 1. In this case, the value is 0 because there is no link between the flux of the two coils. In this case, the value is in between 0 to 1. It also depends on the geometry of two coils. The self-inductance depends on the number of turns, area of the coil, etc. It depends on the distance between the two coils. If the distance is large, then the mutual inductance is small. If they are placed like this, in this case, the mutual inductance is large. If L1 and L2 are in series, then this is the expression. If they are in parallel, then it is the expression. Thank you and have a nice day.